Hi everyone, I'm Dr. Kiran Raavi, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. Today, we're going to discuss MOS capacitor and its operation. Let us see what is the overview of today's presentation. Today, we're going to start with the introduction to the MOS capacitor and what is MOS capacitor, basic structure, and it's then followed by operation. Particularly, it is operated in 4 modes. So today we are going to discuss flat mode operation and accumulation mode operation and conclude with the summary. So coming to the introduction part, MOS stands for metal oxide semiconductor. A MOS capacitor comprises semiconductor body or substrate, an insulator film such as SiO2 layer, a metal electrode called gate. So if you observe this figure, so you can observe, so there it is a 3 layers. One is metal, top layer is metal, and second layer is oxide layer, and third layer is semiconductor layer. The oxide film can be as thin as 1.5 nanometers, so very thin layer. So 1 nanometer equals to 10 angstrom, or the size of a few oxide molecules. So before 1970, the gate was typically made of metal such as aluminum. Before 1970. So hence the name metal. M stands for metal oxide semiconductor. So up to 1970, metals are used. After 1970, heavily doped polycrystalline silicon has been the standard gate material. Okay. So because of its ability to withstand high temperatures without reacting with the SiO2, as temperature increases, few materials may change its characteristics. So therefore, they may react with the other components, side by side components. So for that purpose, so instead of to avoid this situation, instead of metal, we can use the silicon material, that is polycrystalline silicon material, that do heavily doped. It is used in integrated circuits, MOS transistors. So this is, so where we can use this MOS capacitors is particularly in MOS transistors. So individually it cannot be used. So with the integrated circuit, so in the MOS transistor we can use this MOS capacitor, and particularly to store charges in integrated circuits. The capacitance of MOS capacitor varies with voltage applied to its gate terminal, with the body typically grounded during this application. However, so here the body is grounded during this application. When voltage is applied to the gate, across gate, so the capacitance of MOS capacitor can be controlled. So let us see the different operating modes of MOS capacitor. It can be operated in 4 different modes. So flat band mode, accumulation mode, depletion mode, inversion mode, strong inversion mode. So today we are going to discuss the flat mode, flat band mode, accumulation mode. So coming to the flat band mode operation. So that means flat band mode means there is no potential is applied, so there is no movement of electron. So that means no charge particles, there is no movement of charge particles, no electron movement, so no current flow. So the distribution of dopant is uniform and the energy band has a flat band. So see here, so it is a 3 layer. This is the first layer is metal layer, and this is oxide layer, then p-type material, p-type semiconducting material layer. So here, so x is equals to 0. So at this point, there is no external voltage. We are giving no external voltage. So there is no movement of electrons. So hence, obviously, because gate voltage is 0. So you are not giving any voltage across the gate. So therefore, there is no movement of electron. Hence, no current flow. So distribution is uniform, and hence your energy band diagram also, the energy band has flat band. So you can observe here. So these are the flat band so this is initial case flat band. So now you can observe here. So this is energy band diagram, carrier concentration. So this is holes at the equilibrium condition. So this is electrons naught is equals to Ni square. So all are uniform distributed. Now coming to the second mode is accumulation mode of operation. MOS capacitor operated in accumulation mode of operation. So here that means we are giving some voltage. When gate voltage is negative, the SiO2 layer gets polarized. Polarization means the charge particle changes. So positive to negative, negative to positive. So gets polarized. SiO2 layer gets polarized, oxide layer. Separation of positive and negative charges in the dielectric material. What do you mean by polarization? Means separation of positive and negative charges in the dielectric material is nothing but polarization. Positive charges of SiO2 move closer to gate and negative charges move away, because as we are giving gate voltage negative. So as we are giving gate voltage negative, what happens here? The SiO2 layer, positive charges of SiO2 layer move closer to the gate because opposite charges are attracted, and negative charges move away from the gate. Negative charges of SiO2 attract positive holes from P substrate. So this is P substrate. So whatever the negative charges, the electrons, these holes, positive holes are attracted, these holes are attracted towards the gate, negative gate voltage. Holes move up and accumulate under SiO2, and thereby a thin accumulation layer holes appears under SiO2. So here you will get the accumulation layer at the under SiO2 layer. So in between gate and p-type semiconducting material, SiO2 layer is there. Okay, so that forms, so holes move up and accumulate under SiO2, and thereby a thin accumulation layer of holes appear under SiO2 layer. If the gate voltage is made more negative, hole accumulation is increases. So if the gate voltage, so across gate to body, so if you increase this voltage, gate voltage, so what happens? So more amount of electrons from P substrate is attracted towards the gate. So holes are attracted towards the gate, and in between, so you have a silicon SiO2 layer. So under SiO2 layer, so there is a huge amount of holes are accumulated. So those hole accumulation is also increases. So this behavior of MOS device is similar to parallel plate capacitors. So that's why we can say it is a MOS capacitor, metal oxide semiconductor capacitor. So if you further analyze this operation, so you can see the basic capacitance, oxide capacitance is represented with C suffix naught, C naught, and it is given by epsilon A by T. Epsilon A by T means oxide layer. So we have, you can see, so we have three layers, correct? So first one is metal layer. Metal means again polysilicon, polycrystalline silicon, and this is gate material, gate terminal, and this is your body. So here oxide layer, very thin oxide layer is there. So this oxide layer represented, thickness of the oxide layer is very less. Okay, so depending upon the thickness, we can, the capacitance also changes. So that is given by oxide. The oxide capacitance is given by epsilon A by Tx. So epsilon Ox. What do you mean by epsilon Ox? Means oxide, permittivity, permittivity of oxide. So material constant, you can say epsilon. So epsilon ox means oxide, permittivity of the oxide layer into area of the oxide layer. So this is the area of the oxide layer upon thickness of the oxide layer, right? So that is given by oxide capacitance. And how to get the area? Area is length into width. So how to get this length into width means, so see here. if you observe here, so this is 3-layer, this one you can observe here, and here this is metal and SiO2 layer and p-type or n-type semiconductor. This is SiO2 layer. Okay, so in this case, how to get this? So this is W and this is, so this is W and this is length. Okay, and area is given by length into width. So this is one kind of mass capacitor. So in accumulation mode, mass capacitance is constant at C0 and that is given by, so therefore overall mass capacitance is almost equal to oxide capacitance. So that is C0, Cmax, Cmass means capacitance of the mass capacitor is equals to oxide capacitance. So here Vg is equals to 0 and then this is the flat mode operation. So this is flat mode operation of mass capacitor and that will be converted into some accumulation mode. So in this accumulation mode, the gaps are not flat. So there is a curves are there between conduction band and valency band. So this is regarding energy band diagram of mass capacitor when it is operated in accumulation mode. So that's all for today's presentation. So we have started with introduction. We have discussed the basic structure of mass capacitor and what is the behavior of mass capacitor, what it will be used at which application, in which applications it will be used, and then modes of operation, flat mode and accumulation mode operations we have discussed. So probably next topic will be depletion and inversion modes of mass capacitor, as well as we will discuss the characteristics of mass capacitor. Thank you.